In this video, we are going to start our section learning how to do double integrals over non-rectangular regions. So our goals are to do double integrals over non-rectangular regions, and we'll learn how to do that in two different orders of integration. We'll recognize when it's better to use one order versus the other, and then finally to apply double integrals to compute applications over non-rectangular regions. So in this video, we are going to focus on evaluating double integrals using what's called the dy dx ordering. All right, so let's recall that when I have a double integral of a function f of x comma y over some region R, that represents the volume between the graph of our function, which visually might be like this surface here that I have in 3D space, between that graph and the region R in the xy plane. So the region R is kind of the base region in the xy plane that our surface is above. So I'm going to label that base region as R. So in this picture, this is the x-axis. The y-axis kind of extends like this, and the z-axis is the one pointing up. And I've also drawn a separate sketch of just this base region R in the xy plane, because we'll need it in just a sec. Okay, so how do we set up our double integral to get the volume now that R isn't just a rectangle, it's a more general region? So when I set up my double integral, so my double integral of our function f of x comma y, we're putting the dy on the inside and the dx on the outside. In the next video, we'll learn how to switch it. But what I do first is we're going to determine the inner limits of integration, which are based on the dy. Okay, and to do that, we are going to look at a vertical strip through the region R. So let's draw a vertical strip through the region R. So I'll draw an arrow going vertically. I'll draw a dot when it enters the region, keep going, dot when it exits the region, and then I keep the arrow going. So we are drawing an arrow. We are drawing an arrow through R from negative infinity to positive infinity. In other words, we're drawing an arrow through the region and it's parallel to the y-axis because it's a vertical arrow. Vertical arrow because it's a dy integral on the inside. So when I do that, there is some bottom function based on this region. I'll trace that out. Some bottom function. I'll label the bottom function y equals g1 of x. That's the bottom one, the bottom function. And then there's this top function, which I'll trace out in green. So this top function, let's label that as y equals g2 of x, the top function. Okay, so the limits of integration for this inner integral, which are based on what y goes from, the bottom limit is going to be that bottom function, y equals g1 of x. And the top limit is going to be the top function, y equals g2 of x. Okay. And then step 2 is to determine the outer limits. The outer limits are based on the outer integral, the dx integral. So they're based on the values of x. And the values of x I determine more simply based on kind of what's the smallest value of x for this region. I'll label that as A. What's the biggest value of x for the region, which I'll label as B. So those outer ones go from x equals A to x equals B. So the outer ones are constants. They are constants. And those constants are the smallest and largest values of x, because it's a dx integral on the outside in our region R. So conceptually, what is this double integral doing? In my 3D picture, that arrow R that we drew, this arrow through the region R that we drew, I can draw that kind of here, parallel to the y-axis, and then it goes through the region, and then it keeps on going. Ooh, don't love that. Let's have it keep on going. Okay. And what this inner integral does is it says, okay, above that arrow, let's slice our region parallel to the y-axis. Okay, and then let's give this slice a little bit of thickness. So a little bit of thickness. So that little bit of thickness has volume. So the inner integral gives us the volume of a really tiny slice like that. The outer integral then says, okay, now let's take a bunch of slices like that and sum them all up. And when I sum them all up, overall, I'll get the volume of the whole shape. Okay, so in practice, when I write these double integrals, we typically don't write that x equals and y equals here. Usually I'll just write a and b for that outer integral. And for the inner one, I'll just write g1 of x and g2 of x. And it'll be clear from context, well, are they based on y, if that's the inner one, and then x if it's the outer one. So let's do an example. Let us do an example where we actually evaluate an integral like this. Okay, so the problem says let's evaluate this double integral where this base region R is the region in the first quadrant bounded by these two curves. And as we do this, I'll come back and talk about these steps that it mentions on the previous page. Okay, so I have this picture, this 3D picture where I have my x-axis here, the y-axis, and the z-axis. This curve y equals x squared, my parabola is here. The line y equals 2x plus 3 is here. And then this z equals 2xy, that I'm going to do my best to kind of draw in. That's like if I take those walls and imagine I'm kind of connecting these boundary walls with this surface. Okay, I get some sort of surface like this. All right, and that surface, very rough picture, but that surface is like z equals 2xy. So something like this. And I'm finding the volume. All right, so to do that, I'll need to find my limits of integration. So I'm going to need to sketch that base region. So let's sketch just that base region R. So I'll draw my axes, my x and y axes. So y equals x squared is a parabola, upward parabola, where that vertex is the origin. So something like this. So y equals x squared. And then y equals 2x plus 3 is a line where the y-intercept is at 3. And then slope is 2. So it'll intersect the parabola twice. I'm deliberately making it a little bit more flat to make it clear that it will intersect twice. So y equals 2x plus 3. And it says it's the region in the first quadrant bounded by these. So that would be this region here. This region in the first quadrant. That is my region R. So my region R. So when I set up this double integral of 2xy, we're doing dy on the inside, dx on the outside. To find these inner limits of integration, which are based on dy, I draw a vertical line parallel to the y-axis. A vertical line until when it enters the region, then I keep going until it exits the region, then I keep on going after that. Okay, so where it enters the region, that's based on this bottom curve. So the bottom one is this parabola. That goes at the bottom of that integral. So y equals x squared is my bottom curve. And then the top curve, well, that's this y equals 2x plus 3. So y equals 2x plus 3. Awesome. And then for the outer integral, that's a dx. Okay, so that's based on the smallest value of x for the region, which is here. That's 0. So x equals 0 up until the biggest value of x for the region, which is over here. So I'll need to figure out where these curves intersect to find that. So where do they intersect? Where do they intersect? So for both of these equations, I know their equations. I know y equals x squared and y equals this 2x plus 3. Let's set the y's equal to each other. So x squared equals 2x plus 3. I can move all the terms to one side. So I get x squared minus 2x minus 3 equals 0. Then I can factor as x minus 3 times x plus 1 equals 0. Oh, now that it's factored, I can say what x is. It's either 3 or negative 1. So in terms of my picture, well, the negative 1, that's got to be this intersection point over here, which I don't care about because I'm only focused on the first quadrant. And the one I do care about, well, that's the 3. That's over here. So that's my upper limit of integration, x equals 3. Okay, so that's my setup of my integral. So now in terms of how we actually evaluate this, this is where these steps are going to come into play. We start with the inside integral, which is a dy integral. And for that, we integrate with respect to y, because it's a dy integral. And when I do that, I treat x as a constant. So here I'm just saying freeze x, treat it as a constant. Okay, so let's start that process. So I'll get my outer integral, which goes from 0 to 3. Okay, I'm going to start to get a little lazy when I write these. I'll just write the numbers rather than x equals, x equals. And now for the inner integral, treat y as the variable and x as a constant. So the x will just stay there, multiply the antiderivative of 2y, which is y squared. And then now I'm going to plug in the y equals x squared and the y equals 2x plus 3. And my outer integral is a dx integral. Okay, so I can plug those in now. I get my outer integral from 0 to 3. And I plug these in for y. So I'll get x times, first it's 2x plus 3 getting squared. And then minus, I'll have x times, when I plug in x squared, it'll be x squared getting squared, dx. Whew. Okay, so in terms of our steps, notice that after we do this inner integral, which had a dy, and we plug in, now all the y should be gone, only x should remain. Okay, and that's good, that's what I have. Now we got to do this outer integral, which is now just a normal integral from Math 12, from Calculus Part 2. So let's evaluate this. Let us evaluate this. I'll get integral from 0 to 3. I can distribute out 2x plus 3 squared and multiply x to that. If we do that, we will end up with 4x cubed plus 12x squared plus 9x. And then subtract, this other term becomes minus x to the 5 dx. Now that's an antiderivative I can do. Let's see, term by term, I'll get x to the 4. And then I'll get 4x cubed plus 9 halves x squared. And then minus x to the 6 over 6. So it's a bunch of reverse power rule. And now I got to plug in the 0 and the 3. So plug in the 0, plug in the 3. So if we plug 3 into this, I'll get 81 plus 108 plus 81 over 2. And then minus, with this last term, there's a 3 on the top and the bottom that'll be able to cancel. And then I'll be left with 243. That's 3 to the 5 over 2 on the bottom after I cancel the 3. And then I got to subtract what I get if I plug 0 in. If I plug 0 into all of this, I just get 0. And I'm going to trust that we can simplify it. If we simplify this, we get 108. And that's our answer. So that is our process for doing a double integral over a general region that's not necessarily a rectangle. So in terms of our goals for this section, we've learned how to do double integrals over these non-rectangular regions when we have dy on the inside and dx on the outside. In the next video, we'll talk about how we can do it if we switch that order.